This experiment was completed in the year 2011, as was this video. With much editing and 10 years later, it has finally made its way to YouTube. Welcome to my video. Early in 2005, I began an experiment which was designed to compare the speed of light from a beam pointing in an easterly direction with the speed of light from a beam pointing in a westerly direction. My expectation from the experiment was a faster speed of light west than east. This is the basis of the experiment. The device is turned through 360 degrees in the plane of the Earth's surface. The laser beam is split at the semi-silvered mirror, and one half is sent down the flowing water path while the other half is reflected at 90 degrees to initially travel the air path. Both are reflected back along their respective paths and again reunite at the semi-silvered mirror to follow a common path through a collimator lens which expands the beams travelling to the screen where they are shown to interfere. When the device depicted in this diagram is turned between east and west, no interference pattern shift is noted. So if a light speed anisotropy does exist, the wave numbers along each path must alter by exactly the same numbers as the device is being turned. In order to reveal the light speed anisotropy, it was necessary to disrupt that precise balance. All that would be required is some means of changing the fixed relationship between the two paths. That could perhaps be achieved by somehow moving the glass along the line of the laser beam which is travelling through it. But that would be an almost impossible task. The logical solution would be to replace the glass path with a flowing transparent liquid. The speed of light travelling through the liquid would be affected differently as the device was being turned. An interference pattern shift would be expected, but achieving a stable interference pattern would be almost impossible using this type of setup. A completely different approach was required. The setup used in the Fizeau ether drag experiment would overcome all of these problems. Early in the 19th century, in order to explain some astronomical observations, Fresnel hypothesized that the base in which light was presumed to propagate according to ether theory at the time is dragged along with a relatively moving medium at the rate of v times 1 minus 1 over n squared, v being the speed of the medium, n is the refractive index of the medium. Fizeau's ether drag experiment was designed to confirm what was already observed in nature, and that was accurately described by Fresnel's formula. So there could be only one result if Fizeau's device was up to the task. Fizeau's experiment is the basis for my experiment, but the objective now is to demonstrate a light speed anisotropy. That was not possible using Fizeau's device because both light paths are identical and would be equally affected if the device was rotated. During the course of the original experiment in 2005, the water speed through the water tube, or more appropriately, the water laser tube, through which the two halves of the split beam travel, was calculated according to an observed fringe shift which compared with the 20 metre per second water flow rate, and that was fairly pointless because that could only be so if the anisotropy was as predicted. And that figure was wrong because there was a flaw in my reasoning which gave an elevated water speed for the degree of fringe shift. A reasonably accurate water speed was essential. The initial results from the current experiment showed only small fringe shifts that were not easily identified within the interference pattern wobble. Using different mirror configurations and different thickness semi-silvered mirrors gave very inconsistent results. Nothing was predictable. Generally, the shift was in the right direction, but it wasn't good enough to convince a skeptic, certainly not a sponsored one. Something was obviously wrong. Identifying the cause of the problem was essential before any further progress could be made. That quest proved to be a very enlightening journey. The structure of the new device is fairly basic and flaws can be readily identified, but the interference patterns appearing on the screen were initially shrouded in mystery. Where were these patterns generated? Was I consistently using the wrong pattern? These questions clearly needed to be answered before any real progress could be made. With the water laser tube not installed, the mirror configuration that would be expected to provide an interference pattern between the split beams is as depicted in this diagram. Two other significant interference patterns are also generated which can't be attributed to interference between the two halves of the split beam alone. The third beam is necessarily included in the mix to interfere with each of the primary beams and generate the two additional patterns. The only other light source of any significance is the beam which is reflected off the glass face of the semi-silvered mirror. This can be easily identified as a culprit because the orientation of the fringes in the interference pattern generated between the outer glass face reflection and the internally reflected beam, which are both generated from the same beam, will always be perpendicular to the plane of the mirror configuration, and the fringe width in that pattern will be set by the thickness of the semi-silvered mirror glass as well. But it wasn't to be that simple. If the mirrors are set in this manner, the interference pattern from the relationship between beams 2 and 3 can be oriented to become an extension of the fixed width vertical pattern from the beams 1-2 relationship. If the beam source is a helium neon laser, beams 1 and 3 are too far apart to interfere in this case. I tried using a 634 nanometer 10 milliwatt LED laser but found that it just wasn't worth persevering with. The next video clip was taken prior to magnification through the collimator lens. The graduations on the screen are 1 millimeter apart and the water laser tube was removed. And if the returning beams are elevated above the primary beams, as shown in this diagram, while the relevant returning beam is halted prior to arriving at mirror A, the interference pattern generated between beams 1 and 2 is revealed. The laser source is to the right of the image in this case. This diagram shows 2 points of interference between one wavefront from the upper source beam and 2 wavefronts from the lower source beam, which are 634 nanometers apart, being the laser wavelength. The apparent beam sources are 2.6 millimeter apart, which is the approximate distance between the two components of the same beam after it has been first reflected off the outer glass face and then the inner glass face of a 4 millimeter thickness semi-silvered mirror glass, angled at 45 degrees to the incident beam. Using dimensions based on the actual interferometer, the straight line distance from the beam source to any point of interference around each curved wavefront is 4,600 millimeter, which is assumed to be common for both paths. There's an approximate path length difference of 5.7 millimeter between them using a 4 millimeter thick mirror glass, but it's of little consequence. This diagram gives the distance from the baseline to the intersection between the two leading wavefronts. And finally, the adjacent leg of the triangle from the previous example is shortened by 1 wavelength so that the opposite leg coincides with the intersect point of the following wavefront from the lower apparent source. The difference between the opposites in the two triangles is 1.45 millimeter. The fringe width is therefore 1.45 millimeter, but the fringe width given in the snapshot is barely 1 millimeter. My inability to calculate the fringe spacing meant that, unless there was some mistake in my calculations, my understanding of the entire process was flawed. Using different thickness semi-silvered mirrors demonstrated that there was no proportionality at all between the glass thickness and fringe width generated by the beam's 1-2 interference, and that made no sense at all. And the interference pattern lines generated between beams 1 and 2 for some of the mirrors were nowhere near perpendicular to the plane of the light paths, when they clearly should have been. The fringes from a 2 mm thick mirror were tilted by around 15 degrees from that plane. The only possible answer seemed to be that the beam wavefronts had become distorted during the process of reflection within the glass environment. But if the focal points for all parts of a wavefront aren't common, the distorted wavefronts would scatter the beam all over the place. That thought is proven false because no such scattering is evident in the internally reflected beam after it has emerged from the glass environment. With this simple setup, different thickness mirror glass was attached to the end of the tube and rotated. The source of the incident beam was roughly 4.6 metres from the points of reflection off the inner and outer glass air interfaces, which were angled at 45 degrees to the incident beam so that the reflected beam was at 90 degrees to that beam. The 2 mm thick semi-silver mirror was used in the initial tests. Apart from giving a more clearly defined interference pattern, removing the silver coating made no difference. Even if the incident beam is offset from the axis of rotation, or if the glass face is not exactly perpendicular to that axis, which causes the body of the interference pattern to describe a circle on the screen, the same distortion is still evident. The distorted interference pattern remains unchanged as the screen is shifted further away from the mirror glass, so the distorted pattern would seem to be already in the beam. If the wavefronts are not distorted and beams 1 and 2 are reflected off the outer and inner glass air interfaces, the separation of the apparent beam sources cannot be altered. The fringe width is necessarily rigidly fixed. In order to generate these pattern variations, the glass thickness would need to vary enormously during the turning. This video clip shows the distortion in a 3 mm glass sample. In this case, the location of the reflected beam off the inner glass face would need to move in a complete circle around the reflected beam off the outer glass face. And now, the limits of the distortion in a 4 mm glass sample, as is currently being used in the interferometer. An 8 mm thick glass sample was also tested, and it gave a very distorted interference pattern as well. It should be obvious that unless the reflected wavefronts are distorted or the separation of the beam sources has altered, such distorted interference patterns cannot be generated by the two beams when they are projected onto the screen to interfere. One possible solution is that the glass environment develops a harmonic resonance between the two reflecting surfaces where the 1-2 source beam is regenerating as reflection waves. The matter environment is well and truly involved in that process. The regenerating waves will take whatever form the harmonics of the environment dictates. Whatever the case, the mirror glass certainly needs to be tested. When the water laser tube is initially installed and the mirrors have been set as per the original configuration, two bright spots appear in the middle of the screen which overwhelm the interference pattern. They result when the primary beam that initially travels through the semi-silvered mirror is reflected back off the entrance window of the water laser tube and again off the glass face and inner glass silver interface of the semi-silvered mirror. Elevating the returning beams above or below the primary beams is essential. Ring laser gyros provide clear evidence that the two beams travelling in opposite directions around the light paths will phase lock or mode lock in any mirrors where both beams intersect in the same place. Such locking could only occur in the mirrors to the right of the diagram because the returning beams are raised above the primary beams at the mirrors on the left. This mirror configuration overcomes that problem. It also reduces the effects of crosstalk between the two beams via the matter environment of the water path. The beam intensities diminish as they move through the water, so there is some interaction between the water medium and the light. If the beams are linked through the interaction with the water medium and no change is occurring, there's no reason why the whole environment shouldn't fall into a mutually compatible resonance with the beams. That should in fact be expected. Beams 2 and 3 can be separated in the vertical plane, which sets the fringes of the interference pattern in the horizontal plane at 90 degrees to the beam's 1-2 pattern. In this case, the fringe shift direction depends on which beam is set above the other. With slight mirror adjustments, 3 different patterns can be made to appear on the screen: 2-3, 1-3 and 1-2. But such a mirror configuration only leads to confusion. The beams can again be separated in the horizontal plane with this mirror adjustment. The interfering beams are then 2-3 and 1-2. The focal points for beams 3 and 1 are once again too far apart for the beams to directly interfere. In this image, the arrows show the direction of the returning beams prior to magnification. The two sets of diverging curves represent the magnified beams that will be projected onto a screen to interfere. For this experiment, the non-rotating inertial frame of the Earth, or the ECI frame, is assumed to be the base on which light propagates, which is moving at 400 meters per second to the west of the interferometer body when it's fixed to the rotating Earth's surface at Melbourne, Australia. With the water not flowing, when the device is turned between east and west, exactly the same number of wavelengths are added to or subtracted from the water and air paths, because the number of wavelengths along each path is proportional to the refractive index of the medium along each path, as is the speed of light. So nothing changes. Regardless of where the propagation base may be, the turning will have no effect unless the water is flowing. The expected result was about 1/8 of that shown in this animation. When the water is flowing at, for example, 10 meters per second to the west relative to the interferometer body, the flow rate is 390 meters per second east of the ECI frame. When the device is turned so that the flow is to the east, the flow rate is 410 meters per second to the east of the ECI frame. The difference is 20 meters per second. That's the case even if the propagation base is only 10 meters per second to the west. So the 20 meter per second variation is the only thing of relevance in the calculations. The changes along the air path are constant regardless of the water flow rate, so including the air path in the calculations is pointless. Calculating the degree of fringe shift is thus made very simple. For these calculations, the propagation base for light is assumed to be 10 meters per second to the west of the interferometer frame. When the 10 meter per second water flow is to the west, the frame of the flowing water aligns with the propagation base, so the speed of light difference between the two paths is 0. When the water flow is turned to point east, the speed of light difference between the east and west directed light beams is 20 meters per second. But that difference is reduced at the rate of v times 1 minus 1 over n squared, which becomes 8.727 meters per second. Up to this point, the device was turned back and forth for 180 degrees to point either east or west. The entry and exit pipes for the water were through the base of the tubular bearing on which the interferometer rotates. The turning was thus limited to a little more than 180 degrees. A test of the consequences of inaccurate levelling was also provided. For that test, the bar to the right of the image was driven up and down when the attached crankshaft was rotated, which tilted the interferometer axis by 1.3 degrees in the plane perpendicular to the Earth's surface along the east-west line. Using the tilt mechanism, the interferometer frame can be held in a non-rotating state for 10 minutes. The results can now be recorded, of course. These are some examples of the on-screen display. When screen brightening occurs, an upward or downward tilt limit of the interferometer body has been reached. If the brightening is accompanied by an audible click, the upward tilt is on the east side. Otherwise, the upward tilt is on the west side. This is the extent of the fringe shift for the 2.6 degree total tilt angle when the device is pointing along the east-west line. The pressure gauge measures the water pressure near the entrance point to the water laser tube. Water pressure is noted to be nowhere near proportional to water speed. When the device is turned so that the water flows to the east, the lower right direction indicator LED is triggered, and when it's turned so that the flow is to the west, the lower left LED is triggered. The curved array of LEDs at the top indicate water speed and are driven by the current generated in a coil by a magnetised impeller on the inside of the copper tube that's mounted in the water return hose. The signal is fed into a LED audio level display driver. The LEDs were calibrated by pressurising the less than full water storage tank with air, then opening a gate valve, allowing water to flow past the impeller until a 10 litre volume had passed through. The time for the event gave the number of litres per second. Water speed through the 12.4mm inside diameter water laser tube could then be calculated and attached to the final LED illuminated. These are results from different tank pressures. The red line is approximately the average, where the black dot should be. The errors stem mostly from my estimation of the LED fraction for the final LED illuminated. Its average brightness was used to determine that fraction. It's certainly accurate enough for this case. The tilt angle is set to 0 for the next video clip. The device is turned back and forth through 180 degrees, and the effects of acceleration are present when the rotation is halted and then reversed. Even if those effects were removed, the results would clearly be inconclusive. My next thought was that crosstalk through the glass environment of the semi-silvered mirror had caused beams 2 and 3 to become phase locked. The phase locking mechanism in the mirrors of a ring laser gyro is easily broken, and the same should apply in this case. Turning the device at a faster rate could do the trick, but acceleration would then distort the body of the device at each rotation reversal. The only solution was a uniform turning rate, and that required a 360-degree rotation. It was necessary to upgrade the method by which the device is turned. The 0.5 metre diameter 4-wheel circular carriage is mounted on a similar diameter monorail and is belt driven. Two 2mm diameter nylon cords connect each side of the carriage to 2 thin spring steel plates, which are linked together by a steel bar in appropriately sized spaces. A steel plate attached to the top platform of the bearing tube at 2 points on either side of the platform connects to the link bar. There's no other connection. The water return tube for the upgraded unit was necessarily centred on the bearing tube axis, rising vertically to the upper rotating joint before being connected to the flexible return hose. The consequences of turning the device with that attachment had to be tested, of course. This test was done for different pointing directions and no fringe shift was evident. Notice that I'm using enough force here to shift the interferometer tilt mechanism. The process involved here is equivalent to a very minute tilt test using that mechanism. At the time of my original experiment in 2005, I believed that Fizu's interferometer could detect light speed variations because the results simply confirmed a fact that was observed in nature. I was in fact doing exactly the same thing, so a valid interference pattern somewhere in amongst the available choices would surely be present. Now that the orientation problem in my current setup was corrected and the rotation rate was constant, one such pattern was easily identified, and I had no reason to question its validity. It seemed to be exactly as required. The 3 frames of this animation show the consequences of blocking the returning beam 3 or the returning 1-2 source beam. The beams 2-3 and beams 1-2 interference patterns are identified. The beams 2-3 fringes are to the left of the screen. Those are the fringes that will be affected by the anisotropy. In the next 2 video clips, the first task was to identify the fringe sources. The current setup appeared to be producing results which were almost exactly as expected, and it would be highly unlikely that everything would just coincidentally fall neatly into place. The theory was that the constant rotation was keeping everything on the move, thus preventing the interference pattern from falling into a phase-lock state. The only concern was the Coriolis forces acting on the flowing water along the water laser tube. Those forces would vary throughout the turning, although at each east-west line crossing the forces would be common. Reversing the rotation direction would reverse all of the Coriolis force directions, and that would change how the fringes move en route to each east-west line crossing, but the fringe shift between the east and west pointing directions shouldn't be affected. The test proved otherwise. Reversing the rotation direction caused the fringes to shift by the same amount, but in the opposite direction, and that completely annulled the previous result. This failure prompted me to re-evaluate the entire process. In doing so, I discovered that the fringe movement direction when the rotation was later reversed was in fact correct. But neither result had anything to do with the light-speed anisotropy. I was too eager to accept that the elusive anisotropy had at last been revealed. Identifying the source of the problem wasn't too difficult. The pipes carrying the water in and out of the water laser tube ends are also affected by Coriolis forces, and they were not adequately restrained in the plane in which those forces are acting. Minute clearance was also noted at one anchor point as well, which would allow inelastic movement that could account for the entire noted effect. Extra anchor points were promptly added in the plane of rotation. The turning is once again manual, stopping for a short time at each east-west line crossing. The direction indicator LED is momentarily switched off so that proper comparisons can be made. Now, apart from a slight wobble, there's no sign of any fringe movement at all. Two conclusions can be drawn from this null result. One confirms SR, while the other is that my device is not capable of detecting the anisotropy at all. My objective now is to demonstrate that the latter conclusion is correct. This enormous interference pattern variation could not possibly be produced by the two reflected beams off the inner and outer faces of a 2 mm thick glass interfering on the screen onto which they are both projected. In order to generate such pattern variations, this is how the focal points of the beams would need to alter as the glass is being turned in the manner previously described. The pattern is obviously already in the beam when it leaves the semi-silvered mirror glass environment. The focal points where each of the three beams meet an air glass or glass-silver interface are the obvious energy sources which will set the entire glass cavity resonating in tune with them. A set of standing waves will form accordingly. The anisotropy offsets the phase relationship between the beams, but that change would be of little consequence in the global interaction of the entire glass cavity. The driving frequency and location of the beam focal points hasn't altered. The fringe intensity could perhaps vary though. The same problem is inherent in the semi-silvered mirror of Fizeur's device as well. So why did he find a fringe shift? My current mirror configuration causes the 2-3 fringes to move too far and in the wrong direction when the water flow rate is varied. The 1-2 fringes move as required, but that fringe movement can only be attributed to physical distortion in the body of the apparatus because the two beams involved are generated at the semi-silvered mirror and don't involve the water path at all. I'm not suggesting that Fizu's device was not more robust than mine. I can't possibly know that. But regardless of how robust Fizu's device may have been, he could not guarantee that the observed fringe shift wasn't due to physical distortions caused by the changing water speed. Nor could he guarantee that it wasn't due to the water flowing across the line of the beams at the water entry and exit points. Splitting the source beam close to the end of the semi-silvered mirror and adding a front surface mirror to reflect the relevant returning beam, as shown in this image, leaves an air gap through which beam 3 can freely pass. The semi-silvered mirror glass environment is now of no consequence at all. The added mirror can be set to cross the beams at any distance, but there's not the slightest sign of an interference pattern anywhere. If the fringes are not generated in the semi-silvered mirror glass environment, where are they generated? Truth is an unforgiving master, and false realities will prove to be the catalyst for our pending demise. If there is to be no future for us, all that mankind has achieved amounts to absolutely nothing. So, good luck, and thanks very much for your time. Two 10-metre by 25.4mm bore hoses connect the water pump to the interferometer via the water storage tank. Gas trapped in the much improved window holders of the water laser tube is drained away through small holes drilled through the top section of each window, which are vented into nylon tubes that feed into a lower water pressure zone. All gases trapped in the system is expelled from the uppermost surface of the water storage tank. The water pump drive shafts are 25.4mm diameter. The screws are 2-start 76mm diameter by 32mm pitch. They are 60mm between centres. The pump runs at twice engine speed. A minor flow of water is maintained through the system, which enters on the low pressure side of the pump and exits through a restricted opening at some point in the water circuit where gas contaminants would be expected to collect. The contaminants are thus ejected. With the pump not operating, the inflow and outflow rates are set so that the entire water circuit is pressurised to 40 psi. The reason for the preload was to stop the water from becoming aerated during its turbulent journey around the water paths. The pressure will obviously reduce to some degree in the low pressure side of the pump when the pump is running, but 40 psi works quite well. Prior to fitting the water laser tube, its windows needed to be aligned in the plane perpendicular to the laser beam path. That's done by reflecting a laser pointer off a window face while the tube is rotated around an axis through the centre of the tube. Any misalignment causes the reflected spot to scribe a circle around the screen onto which it's projected. The window is adjusted until the reflected spot remains still. Minute changes attributable to a set pattern of hot and cold areas within the garage environment could perhaps warrant some kind of analysis. But all I managed to achieve when I breathe on the front or rear ends of the water laser tube from close range on a cold day is to fog up the mirrors. Directing a 2000 watt fan heater onto any part of the apparatus from a metre away causes the pattern to wobble about, but the average position of the fringes doesn't change.